Hi, welcome back. Let's have a look at leakage rates and the system volumes. This is all to do with the new IGEUP1B, which becomes mandatory after October 2026. So having a quick look at the values on the right hand side, you can see the maximum permissible leakage rates now depend on the system volume. So that's the volume of the pipework and the meter, all added together using the correct formulas. However, there is a reality to all this and why IGEM has put this new system together. So along the top here, the system volume in meters cubed, you can see the 0.035, the 0.15, the 0.1 and the 0.05. And for them, their leakage rates become 1 millibar for the larger system, 2.5, 4 millibar and 8 millibar. Now our test time is 2 minutes, as you can see on the next row, and I've put a little leak in there. So my leak is 0.02 litres per second, which then equates to 72 litres per hour. However, the interesting part is in the millibar drop on the water gauge where the blue arrow is. You can see that for a smaller system, 0.205 system on the right hand side, that my leakage rate that would show on the water gauge, because there is a smaller volume of gas in the system, is 0.48. So that's almost half a millibar drop that I would register at that point. If the system was up at the 0.01, then I would be recording a quarter millibar drop. So that becomes a no discernible drop, that quarter millibar. Again, if we move up to the slightly larger system of 0.015, you've now got a 0.16 millibar drop. Again, that's no discernible. And then lastly, the 0.035 system, meters cubed, has got a pressure drop of 0.07. So all of these systems are leaking the same amount of gas. We've got a leak size of 0.02 litres per second, or 72 litres per hour, which will dissipate. But the tolerances that we've got there are hugely different in what we will see on the water gauge. As I said, 0.0, almost half a millibar on the very, very small system, and I'm seeing next to nothing on the very, very large system. So the only other way that IGEM could have sorted this out was to change the tightness testing times for each of the systems, but that would be far too complex. That's how it's done commercially. So we can do that here. So on the small system, if I keep that at 2 minutes, we've got double the volume of the size. So if I change that to 4 minutes, then you'll see that my leakage rate or my drop on the water gauge would be the exact same now. And then if this system here is 1.5 times bigger, so we'll change that to 6, and again you can see that comes up, and this one is 14, so it's 7 times bigger. So this just shows you that I would need to do my tightness test for 14 minutes on a larger system in order to show the same amount of drop on my water gauge as tightness testing on a smaller system for 2 minutes. So this is the way it's done commercially. As we said, the issue with this is there would be far too much to do to work out to calculate. So IGEM have simplified this by simply putting in the information to say that if we do all our tightness tests in the 2 minute periods, then my allowances will be larger for the 8 millibar for a small system, 4 millibar for a slightly larger system, and so on and so forth. If I recalculate this to the maximum leakage size that we could possibly have, so 0.3333 is round about the maximum leakage size that I could have. So you can see that that ties in. For the small system, we would have an 8 millibar drop. For the next system up, the volume was 0.01, we would have a 4 millibar drop. This one's slightly out. We're allowed a 2.5 millibar drop, and it's 2.67 is what we're getting. And again on here, we're only allowed a 1 millibar drop. We're at the 1.14. So thinking about that, we're 0.33, almost 0.34-ish litres per second. Calculating that up would be 1,199 or almost 1,200 litres per hour leaking into the system. I hope that helps explain the process for the leakage rates and the volumes and the calculations that we do. Quite simply, if we have a leak that is less than 0.025, a no discernible pressure drop, then we can pass that system. But 0.025 millibar drop in pipework is still an acceptable pass. This would mean that my leak on a smaller system would be less than 0.01, and I'd only be losing 36 litres per hour. Just to finish off this video, a quick question on temperature stabilisation. So what difference does temperature do to the pressure in a system? So using Gay-Lussac's law, we can see that if we have a 1 degree temperature difference, 20 degrees, 90 degrees, and that doesn't matter whether it's going up or down, then that can make a difference on our atmospheric pressure against the gas pressure of 3.5 millibar. So if the temperature's going up the way, that would be a 3.5 millibar rise. If the temperature's going down the way, that would be a 3.5 millibar drop. We could change this. Even 19.8, so a 0.2 millibar difference is going to make a difference of 0.7 millibar drop on your water gauge. So temperature stabilisation, we've always said in our teaching that 1 minute is a minimum time. We may need to let it stabilise longer.